let's try to solve this problem here. So the figure shows 2-point charges Q1 with 30 microcoulomb positive charge and Q2 with 90 microcoulomb positive charge placed at 1.2 meter apart. So Q1 and Q2 are placed 1.2 meter apart, as shown in the diagram over here. So now they say find a location along the line, this line over here, joining the two charges. So we have a line joining two charges as shown in the dotted line in the diagram. And now they want you to find a location on this line where the electric field is equal to 0. So they ask, at what location along this line can you find the electric field to be equal to 0? So later we have to write where is the position where the electric field is equals to 0. So let's try to draw a diagram, copy out the diagram first in order to see where is it possible for the electric field to be equal to 0. So I'll say this is Q1 and it's 30 microcoulomb. And you have Q2 over here. And it's 90 microcoulomb. So I'm going to draw a dotted line in between the two charges. Okay, so now the position where the electric field can be equal to 0 must be on this line, because that is what the question asking for. And they say that because it's on this line, so it can be anywhere along this line. Okay, so let's try to see where is it possible for the electric field to be equal to 0. Let's try 3 different positions. One position over here, one position over here, and one position over here, to see where is it possible for the electric field to be equal to 0. Okay, we are testing things out. This is just a tip, just to share with you how the idea. Okay, if you are in an exam setting, or if you are doing exercises, you don't need to do this, but I'm just showing you the concept. Okay, so let's try to pick this point over here. It can be anywhere on this line. So let's try to pick this point over here, see whether it's possible for electric field to be equal to 0. Okay, so I'm going to use green pen. So this position over here, let's put a cross over here to show I'm looking for the electric field at this position. Okay, so at this position here, the electric field will be an overlap of the electric field produced by Q1 and electric field produced by Q2. Q1 will produce its own electric field, then it will cover the whole paper that you are seeing right now. Q2 is also a charge, so Q2 will also create its own electric field covering the whole paper over here. So the whole paper here has electric field, which is an overlap of the electric field produced by Q1 and the electric field produced by Q2. These two electric fields will overlap with each other in this region over here. So let's try to determine at this specific point in the region, what is the direction of the electric field produced by these 2-point charges. These 2-point charges are the one that creates the electric field, and you want to find the direction of the electric field at this position over here. Okay, so we know that if the electric field is produced by a positive point charge, then the electric field must be pointing directly away from the point charge. If the electric field is produced by a negative charge, then we know that the electric field at any position will be pointing directly towards the point charge. Okay, so let's try to determine the electric field produced by Q1 first. So Q1 is a positive charge. That means that the electric field produced at any point in the region must be pointing away from this Q1 over here. Okay, so if we are looking at the position over here, we are interested with the electric field over here. We know that the electric field produced by Q1 over here must be pointing away from Q1. So pointing directly away from Q1 will be like this. Let's call it E1. Okay, how about the electric field produced by Q2? Q2 is a positive charge. So again, if you look at any region on this paper, pinpoint a position, and you want to know the electric field produced by Q2 at that point, you just need to point directly away from Q2. And that's the direction of the electric field produced by Q2. So we are interested with this point over here. We want to determine the electric field produced by Q2 at this point over here. So we know Q2 is positive charge, it must be pointing away as well. So E2, the electric field produced by Q2 will be pointing in this direction. So now if E1 and E2 are pointing in the same direction, so if they are pointing in the same direction, no matter what value E1 is, no matter what value E2 is, if you sum them up, it's impossible to be zero. Okay, it's impossible to add two vectors that are in the same direction. You add them up, they can equal to zero. It's impossible to do so. Therefore, we know that our point, our location, the location of interest is not here. The location where E is equal to 0 is not here. Because here it's impossible for you to sum up E1 and E2 to be 0. Okay, so now let's change our focus to this another n over here. Okay, so let's simply take a point over here and try to determine the electric field produced by Q1 and Q2 at this point over here. Okay, as usual, Q1 is a positive charge, so the electric field produced at any point in the region should be pointing away from Q1. Q1 is the one producing the field. Because Q1 is positive charge, the field will be pointing away from Q1. So it will be pointing in this direction. This is the direction away from Q1. So this is the electric field produced by Q1 at this point. Q2, how about Q2? Q2 is a positive charge. So again, the electric field produced by Q2 will be pointing away from Q2 itself. So at this point, the electric field produced by Q2 will be pointing away. Also in this direction. So now E1 and E2 are in the same direction. That means that no matter how you add E1 and E2 up, it's impossible to be equal to 0. The vector sum can never be 0. So this location is impossible as well. The location is not. The location where E is equals to 0 is not here too. So where can it be? Well, it has to be in the middle region, right? So let's try to simply take a point in the middle, then try to determine whether it's possible for the electric field to be equal to 0. Well, the electric field produced by Q1 will be pointing away from Q1. So at this point over here, the electric field produced by Q1 will be pointing away. That means pointing to the right in this case. This is E1. How about the electric field produced by Q2? Q2 is a positive charge, so it must be pointing away. The electric field produced by Q2 must be pointing away from Q2. So pointing away will be pointing to the left. Now, if you look at this diagram over here, you see that E1 and E2 are pointing in the opposite direction. So it's possible that if you add them up, the answer can be equal to 0. You just need to make sure the magnitude of E1 and the magnitude of E2 are equal. If they are equal magnitude but opposite direction, if you sum them up, the net, the final electric field will be equal to 0. And that is what we are looking for, the location where the electric field is equal to 0. Okay, but where is the exact location? Is it here, or is it here, or is it here, is it here, is it here? Well, that is what we want to determine. If the point is too close to Q2, then the electric field produced by Q2 will be larger than the electric field produced by Q1. If we are too close to Q1, then the electric field produced by Q1 will be larger than the electric field produced by Q2. So we want to find a point where the magnitude of E1 and the magnitude of E2 are equal. And then if you manage to find the distance for that position, we are able to get the answer over here. Okay, so let me clean up the diagram a little bit so that we are able to focus on what should we do now. Okay, so we know that the magnitude of E1 and the magnitude of E2 should be equal to each other. So that is what we want to do now. So we know that E1 must be equals E2. Again, cannot put vector sign on top. The direction is opposite. So the direction, if the direction is opposite, then they are not the same direction. They are not equal. Only the magnitude is equal. Okay, so the electric field here is produced by a point charge. It's produced by Q1, it's produced by Q2. Both of them are point charge. So the electric field produced by a point charge can be written as K Q1 over R1 square equals to K Q2 over R2 square. So just by looking at this, we know that there are some stuff that we can cancel out. We can cancel out the K. Okay. So now we have to put in values into the situation. Q1, we are not going to take the sign. We are going to just take the value. It's 30 microcoulomb. On the other side, Q2 is 90 microcoulomb. But what about R1 and R2? We don't know where is the point. It can be here, it can be here, it can be here. We don't know where is the point. So what do we need to do here is we have to arbitrarily take a point. So let's just take this point. Okay, we don't know where is the point. We just pick a point. Then we call that point to have a distance of x. You want to call it what? Y, z also can. There's a distance of x from Q1, and the distance from Q2, it's 1.2 minus x. Okay, then you add x and 1.2 minus x, you add them up, you get 1.2 back. Okay, so you did something similar in semester 1 as well. Okay, so what you need to do is R1 here, you know that it's x squared. R2 here, it's 1.2 minus x squared. Okay, now we have done this. Let's try to simplify the situation over here a little bit. We are going to cut out the micro part. Because left hand side got micro, right hand side got micro. They can cancel out like this. Then what we need to do now is rearrange the equation. Rearrange the equation will help us a lot. Okay, we bring the 1.2 minus x, this thing, whole thing, bring it up to the left hand side. So it will be 1.2 minus x squared divided by x squared. On the other side, there will be 90 divided by 30. Okay, so you can see this whole thing here can be put under one square bracket. Then this thing here is just 3. So if you do square root both sides, you end up with 1.2 minus x divided by x. You already square root both sides. So on the right hand side, you have square root of 3. Now, if you put this into your calculator, or you want to rearrange first before you put it into your calculator, it's fine. You end up with the answer x is equals to 0.44 meter, 0.435 something. Okay, 0.44 meter. So what does it tell you? It tells you that this value here is 0.44 meter, and on the other side it's 0.76. Okay, so we know the distance already, but what they're asking for is not the distance. They're asking for a location. They ask you to find a location. So you have to describe clearly where is the location where the electric field is equal to 0. Okay, so we can write the location where E is equals to 0 is in between Q1 and Q2. Okay, we've specified that it's in this region over here between Q1 and Q2. Then we also say that it is 0.44 meter to the right. of Q1. So state that it is in between Q1 and Q2, but it's 0.44 meter to the right of Q1. So that's how you specify the location where the electric field is equal to 0. Okay, so if you go slightly to the right of this position, then you get electric field not equal to 0. If you go slightly left to that position that you find over here, you also get electric field not equal to 0. Only at that point the electric field is equals to 0. And this is how you solve this question over here.